there's not as much content for radiation, so that's why I say I got first I can do that. It's just the next couple of weeks are really busy for me. So yeah, I can promise you the radiation one, but the first unit I'll see by a plan. Okay.
Did you do it? No, really? I can't make it long. No, I just haven't signed it. It's just trust me. Yeah, I really hate wow. So Nick, when you let me write one second. Sorry, I totally right. My dad would be talking on his part. This is a really small time. No, if it wasn't sport bike, maybe I would have. Yeah. She's already up. Right now? No. Oh, like 6? Sure, but I gotta start on the oh my god. I told you, bro. I ain't gonna look at it. Oh wait, I might not be able to just I'll be on the way on. Yeah, 7. What? What you doing? I don't know. Maybe work some data with us. He's done already. I know exactly. What do you guys spend all day Saturday and Sunday night doing? Yeah. Oh, that's good. Never timed it. Actually, Sam, it's been like 2 literally drinks water. I am cold. So when I came back, I came back and I did chicken. I just started bro. I opened up my phone. All right. So. Wait, she's going off. Did we really left it unread? That's why she asked that. This has been some family. I can't just let it go. No, it's hard to hey, but I'm not saying use it. I'm giving this to myself. No, wait. This is a family game. You're so loud, bro. That bro, you make it sound like I have apology. Like by the time he'll like need a try to break something. Get invested to like fall out. You know what? Bro,
Hey Kevin, how's it going?
Still sweating.
Oh. Wait, what? Oh.
So you gotta find.
Hey, how's it going? Sure. Yeah.
I'll be on the lecture later.
Okay.
It's
Yeah, yeah, no
okay,
problem.
it's okay, don't worry, I don't wanna go to sleep yet.
No, Thursday.
How you doing, Professor?
Oh, good. Good. Tired, but I'm sure you guys all are at this point in the semester.
Today was showcase, I think, for the senior.
Yeah, yeah.
That's pretty cool. Sorry, Professor. That's good.
Yep, no problem.
Have a good day.
You too. He had to leave. He's gonna leave early, and so that's why I got him get it. But everyone else are gonna wait till the end.
Yeah, electronics. Right,
Yeah, yeah. So he had to leave early, so I let him get it. But everyone else, I'll get back at the end of class. Yeah.
Make sure you don't get it. No, I haven't touched it. I haven't touched it for. Right, no. I was just go home. I can't. Don't worry, this was. We'll do some fighting. So what, over 10, Paulo and I are not too far. Caesar could be the look, I did. No, Caesar could be this. Yeah. We gotta talk about it. Stop being safe. I know you do. Do you actually know? We gotta turn it. If I don't get back by then, I'm gonna say our friendship is void. Where'd you get? I don't know. I don't think so. Okay. So I'm saying, no, I. Yes. Just. Why don't we just pick up? Doesn't matter. What? See that? Yeah, I know, it's really. I watched this in my. I watch things. I just speed read. Today, I'm probably saying. I read this one. I made him.
All right, it's 2:30, so let's go and get started. All right, good afternoon, everyone. How's everyone doing today? Doing good, doing good. Week 15, so we got 2 more weeks to go. So we have 4 more lectures, and so today, Wednesday, and then next week, and then that's it. And then we might never see each other again. No, I'm kidding. I'll be here. Okay, so of course, you know, I know the thing on everyone's mind is the midterm exam. So I actually graded them on Saturday, but I didn't want to get emails over the weekend, so I waited till this morning to post it. And so everyone probably noticed it this morning. And so the average was good, actually. So, you know, you guys are north of 70% on the convection midterm, which is strong. And so just for comparison, you know, the last time I kind of taught the class in the same way as this was 2019. For that midterm, which I thought was easier than your guys' midterm, their average about 67. So you guys are doing pretty good for this one. Okay? So of course I have the exams with me today, and so you guys can pick them up after the class. I have your cheat sheets too, and so you can pick that up as well. You know, and so, you know, I posted the midterm solutions, and so, you know, please go through your exam. Make sure you kind of understand the feedback that I gave you, and if you have questions on, you know, if I added the points up incorrectly, or if you want to ask, or if you think you deserve more points, then please let me know. You know, I'm always happy to talk about those things with you guys. Okay, and so at this point in the semester, you know, a lot of the grades are in, and so, you know, we have 1 more homework assignment, and of course the final exam. And so I think now is kind of a good time to kind of look and see where you're doing in the class. And if you are where you want to be, that's great. But, you know, if you want to improve your grade, then, you know, of course, come talk to me as well. And, you know, we can have those conversations over the next couple of weeks. Okay. All right. And so with that, are there any questions I can answer about anything before we start? Okay. All right. So let's go ahead and get started with the lecture today. So the topic for the lecture today is radiation exchange. So I kind of alluded to this at the end of class last time, okay? Because so far, you know, as we've talked about radiation, we've only just talked about kind of one surface at a time, right? Or more specifically, we've focused mostly on just how much heat can an object give off in radiation, okay? Of course, another word for the amount of radiation an object gives off is emission, right? So we've been focusing mostly on the emission side. Radiation is a two-way street, right? Just like any kind of heat transfer. And so if an objects are emitting radiation, that means other objects are absorbing it, okay? And this constant interplay between, you know, emission and absorption, you know, that constitutes what I call radiation exchange, okay? And so from here on out, and so starting today, and probably for next week as well, you know, we're going to talk about how objects actually, you know, exchange heat via radiation. Okay? And I think these last 2 weeks are nice because, you know, I would say, you know, for so far what we've covered in radiation, it's kind of been almost separate from everything we've done in this class, right? So we talked about optics, we talked about wavelengths and intensities and all that stuff. And so, you know, we haven't really talked about heat transfer really at all. So, you know, these last 2 weeks are kind of where it all kind of pulls in, and we can actually relate this to some of the other concepts and methods that we've talked about in this class, okay? Unfortunately, you know, when we talk about radiation exchange, things get a lot more complicated. And so there's a lot more factors that come into play. And so in order to simplify these and in order to basically in order for us to be able to study this in the last 2 weeks that we have to make some more assumptions. Okay? And so if you look into the lecture notes, I actually have quite a bit there to talk about these assumptions. But for this year, I want to focus mostly on just doing the problems themselves. And so we're going to talk about what the assumptions are, but I'm not going to do a lot of the motivation behind them. Okay? Basically, the two assumptions that we have to make is that we have to assume that our surfaces, at the very least, are what's called diffuse and gray. Okay? And we'll go through what each of them mean. Okay. So let's start with diffuse. Okay. And so to understand diffuse, we have to kind of go back to our spherical coordinates just briefly, right? So we know that kind of the natural way that we describe radiation is we use spherical coordinates, right? Because an object will kind of expel radiation in all directions equally. Okay. What the diffuse assumption basically means is that the radiation that you emit and absorb is independent of direction. And so in spherical coordinates, we have basically 3 coordinates in spherical coordinates, right? So we have the radius, the radial component. We have the polar angle, theta, or excuse me, for this class we use phi for the polar angle. Okay. And we have the azimuthal angle, theta. Okay. And so what the diffuse assumption basically says is that we're going to ignore any variation in phi, and we're going to ignore any variations in theta. Okay. And so the radiation is going to be strictly just a function of distance. Okay? Okay. And so that's what diffuse means. And so diffuse means it doesn't really matter what direction that we're facing it. And so if you're having radiation coming in from one direction versus another direction, they're going to count to be the same. Okay. Okay. And so generally, whenever you make assumptions, the question is always, how reasonable is this assumption? And like, how often does this occur in real life? The diffuse assumption is pretty reasonable most of the time. And so you can assume, your object is diffuse, and no one's really going to give you any hassle for it. Okay. If I'm not mistaken, then if you want to look at situations where the diffuse assumption isn't valid, you kind of have to concoct them yourself. And so in other words, you kind of have to try to kind of break this assumption. But if you're talking just general everyday situations, or even in a lot of engineering situations, diffuse is usually pretty good. Okay. Okay, so that's the first assumption we have to make. The other assumption we have to make is we have to assume our surface is gray. And so what the gray assumption basically states is that your emissivity epsilon and your absorptivity alpha, both of these are independent of wavelength. Okay? Okay. Remember, wavelength was our variable lambda. Okay? And so wavelength is usually very important when you're talking about optics, right? And so that determines whether you're in, the infrared spectrum or your ultraviolet, the visible light, right? And we saw last time that, the radiation intensity or radiation emissive power depends really strongly on the wavelength, depending on its temperature, right? And so the gray assumption is basically going to say that, we're going to ignore those dependencies, okay? And so, of course, we spent, the last week and a half talking about how wavelength is really important. And so if we're now going to neglect this, this is actually a pretty strong assumption, okay? In other words, this is one that you'd have to justify, or one that, if you're looking at real life situations, this one may not be true because, the radiation does depend very strongly on the wavelength. But we kind of need to make this assumption now, just so we can get the ball rolling. Okay. All right. So we won't. And so, I'm not going to go through, how these assumptions kind of play too much of a role, because that kind of involves going into much more of the theory of optics. But, I did want to get more into, how do we actually use these things. But I did want to make you aware that, we are making these assumptions, and just kind of a very general overview about what they mean. Yeah.
The theory behind these assumptions were in the lecture.
Yeah, these are in the lecture notes. And so if you want to learn more about these, then you can look at that, because that involves something called Kirchhoff's law and kind of what that kind of motivates. And it kind of goes a bit deeper into the assumptions. And then the textbook, of course, goes a lot more deeper into these as well. Yeah. But after kind of looking at these notes again and knowing that this is a class in heat transfer, it's not a class really in optics and lasers and stuff. And so let's get as quickly into the heat transfer stuff as we can. But before we do that, I need to kind of make sure that we're very clear about all our assumptions. Okay. All right. Any other questions on this? Okay. All right. So then let's go ahead and jump into it. Okay. And so generally speaking, so now that we've kind of stated our assumptions here, we are ready to start analyzing these heat transfer situations. Okay? And what we'll see is that when we're talking about radiation exchange or the exchange of heat via radiation, they depend on three principal factors. Okay? One being the geometry and orientation of the surfaces. Two being the radiation properties. Okay, so those are things like the emissivity and the absorptivity. Okay? Okay. And 3, of course, is surface temperature. Okay. All right. And so I would say so far, we have a pretty good handle on 2 and 3. Okay. And so we spent, a long time talking about, what the emissivity is and what it and how it affects things, right? And absorptivity a little bit too. And of course, we understand surface temperature because, this is a heat transfer class. And so, we've been dealing with this a lot. Okay. And so the only factor that hasn't really been accounted for yet is geometry. Okay. We talked about it a bit, when we talked about solid angles and such, but nothing really practical yet, right? And so, we want to really put this in a practical way so that we can actually perform heat transfer calculations. Okay? And so that's what the focus of this is going to be. And kind of the general way that section 1 here, or point 1 is accounted for, is through this property known as the view factor. Okay? And view factors is a pretty core concept of what we're going to be working with over the next 2 weeks. Okay. Okay, so what is the view factor? So view factor. Okay. And usually we give this symbol F sub ij. Okay. And so the way that we define this is that it's the fraction of radiation that leaves surface I that is intercepted by another surface j. Okay? Okay. And so when you talk about view factors, it's always paired. And so there's always two surfaces to account for. Okay. Right. So I can give you kind of a visual representation. And so let's say that this is object I, right? Let's say that we have another surface here. We call this surface J. Okay. And of course, surface I right here is going to be emitting radiation in all directions, right? Because that's what objects do. They emit radiation in every single direction. Okay. And so of course, when I draw the objects like this, it's pretty obvious that not all of the radiation from surface I is going to hit surface J, right? So only a fraction of these. And so, let's say that maybe these two. Okay. Only these two radiation beams, and all the beams in between, those are what's going to hit surface J. Okay. And so all the view factor is expressing is the fraction of these radiation beams that hit the other surface. Okay. And so we can quantify this. And so what we say is that Fij is equal to Qij, okay, where Qij is the amount of heat that gets transferred between surface I and surface J via radiation. Okay. And this is divided by Ai, Ei. Where AIEI, that product is the total amount of radiation that that object is emitting. Okay. Let me go ahead and define these. So Qij, this is okay, so Qij, that's the actual, you can think of that as like the actual heat transfer that goes from I to J. Okay. And AIEI, where this EI here is sigma Ti to the 4th. Okay. This is the total amount of radiation, or I guess there's this one in there too. Okay. Okay. And so AIEI is just the total amount of radiation given off by surface I. Okay. And AI there is surface area. Okay. And so that's the idea of the view factor. And so the view factor is basically just a way, an easy way for us to quantify, how much radiation or the fraction of radiation that comes off of one surface that goes to the other. Okay. And so typically, typically the way these problems work, or typically the way these go, is that you can compute this denominator, right? Because that really only depends on the geometry of object I just by itself, right? So as long as you know the surface area of the object, and as long as you know its surface temperature, you can compute that. Okay. The view factor, actually, you can determine this as well. And so there are ways to compute this that we'll go over soon. You can either compute it by looking it up in a table, right? And so a table is going to have certain view factors and certain geometries. Okay? Or there are other ways to do it as well. Okay? Or based on rules. Okay? I'll just leave rules in quotations just because it's we'll go over that soon. And so what you usually do is that if you want to compute QIJ, right? So that most of the time that's what you're interested in. You're interested in how much radiation is or how much heat is being exchanged. You compute the denominator here. You look up Fij in a table, or you compute some other way, and then you use those two things to compute Qij. Okay. All right, so that's kind of a sneak preview of where we're going to go, and also kind of what the view factor kind of physically means. Okay. All right, any questions on this? Okay. Okay, so let's go over some of those. View factor rules. Okay. Because these rules will help you determine, how many or how to compute some certain view factors. Okay. Okay. And so the first view factor rule is known as the reciprocity relation. What did I call it that? It's just the reciprocal relation. Must have reciprocity in the book. It's not a word. Okay, so the reciprocal relationship basically says that if you have two objects, then their view factors, their conjugate view factors are reciprocals of each other. Okay. Okay. And so if you have two objects, so let's say that we have Fij, right? So we have a surface I, surface J. Oftentimes we want to see how that's related to the opposite of that. So Fji, okay? And oftentimes these two are not the same, right? And so they're not going to be totally the same with each other, okay? But they are related. Okay? And so the way that we relate them is according to the following relationship. And so what we say is that if we take Fij and we multiply by Ai, okay? So that's the area of object I. And notice how the area on that side is matched with the first index, okay? Wait a second. Yeah, it's AJ. Yeah, and so if we on the other side of this equal sign we multiply Fji by AJ, what we say is that these two are related to each other. Okay, in fact they're the same. And so if you factor in the areas into account, then you can compute the other view factor based on one that you may already know. Okay. And so if you're given a problem where you have one of the view factors, it's either given to you in the problem, or you can compute it from other ways, then you can use that to find the reciprocal, okay? Because oftentimes these are not going to be the same. And that'll be more clear once we, once we do an example. Okay. So that's the reciprocal relation. Next is the, I guess it doesn't have an official name, but I like to call it the completeness rule. Okay. Right. So this specifically has to do with certain areas that are what I call enclosures, or in other words, you could call them kind of closed spaces. Okay. And so for closed spaces, so this can actually be a physical enclosure, and so it could be physically like a box. Okay. And so in other words, if you have a surface that surrounds an object, or you can kind of draw your own enclosure, and we'll do a lot of examples on this later. Okay. But in other words, you have to have a closed space. Okay. So i.e. single curve bounds the domain. Okay. And so if you can take basically a single line and draw that around your domain, almost like a control volume, if you remember that from fluids, then I would consider that a closed space. Okay. In these situations, if you sum up all the view factors, they have to equal 1. Okay. Right, given that I is fixed. And so mathematically it looks like this. And so if we take the summation of j, okay, from j is equal to 1 to n of fij, okay, so I is fixed, and so we're not summing over I, we're only summing over j, okay? J here being the target surfaces, okay? This has to equal 1, okay? If they aren't equal to 1, then you don't have a close situation. Well, yeah. I'll draw a picture on this. I think it'll be more clear if I draw a picture. Let me add this kind of tooltip. Okay? And so we sum over all the receiving surfaces. Okay. So let me draw a picture for you just to make it a bit more clear. Okay, so let's say that we have a well, let's say we have an open box. Okay. And so I'll call this surface 1, I'll call this surface 2, I'll call this surface 3. Okay. Okay, so we have 3 surfaces and 1 open part. Okay. Okay. And so just this by itself, you would think it's not a closed surface, right? Because we have an open part. Okay. But we can draw kind of an imaginary enclosure around this, right? And so if we took a line, we kind of drew it all the way around. And so we kind of artificially close the domain, right? And so that the dotted line is not anything physical. And so that dotted line is not, a surface, but we use that to kind of enclose our surface. And we kind of make a 4th surface right here, okay? F4, or surface 4. What the completeness rule says is that, if we consider just surface 1 as the emitting surface, okay? And so if we take the summation F11 plus F12 plus F13 plus F14. Okay. All of the sum of all these things has to equal to 1. Okay. And the same goes for all the other surfaces as well. And so that's not unique to surface 1. So if we take surface 2 as the emitting surface, and so we do F21 plus F22 plus F23 plus F24. Okay. And so here we're considering surface 2 as the emitting one, and then we're summing up all of the possible receiving surfaces. That has to equal to 1 as well. Okay. And so for any given emitting surface, if you sum up the view factors of all the possible recipients in a closed space, then they have to equal to 1. Okay. All right. And intuitively, this makes sense too, right? And so, when you consider this closed space, or space that we close, by design, right? Because it's a closed space, that any radiation that comes off one, like it has to go somewhere, right? It can't just come up to the middle and be like, no, I quit, and then just stop right there, right? It has to keep going until it hits another surface. And so if you have that in mind, then it has to be intercepted by another surface eventually, right? So whether that's surface 2, surface 3, surface 4, or even coming back to itself, and we'll talk about that in a second. Any radiation that comes off one has to go somewhere. And so that makes sense that the view factors, then they all have to sum up to 1 in this case. Okay. Okay. And so this enclosure rule or this completeness rule kind of is based on that fact. Okay. And so this is another rule that you can use to determine, certain view factors. Okay. Okay. All right. Any questions on the completeness rule? Okay. Okay. And so those are the two main rules. And so those are the ones that you can use mathematically to determine some view factors. I do have a third rule. It's not an official rule, but I think you use this one kind of more than the other two, honestly. And this third rule is called inspection. Okay. Sounds like a Dungeons and Dragons skill that you have to use. But basically, inspection is kind of kind of your way to kind of use your intuition to determine some view factors kind of automatically. Okay. Okay. So I make this kind of an official rule because if you look into the textbook, they'll use the word by inspection. So by inspection, this shape factor is, this view factor is 1, because obviously, right? And so let me give you a couple examples of of some that you can do by inspection. Okay. And I'll take this opportunity to explain these ones as well. Okay. And so the view factors with the double index. Okay. Okay. And so these are situations where FII, okay? Right, and so what this means, and so when you see a double index view factor, those indicate situations where the surface is emitting radiation, and then it's that radiation is hitting the surface again by itself, okay? And so you might ask yourself, how is that possible? Okay? And so generally this is only possible if your surface has a certain type of geometry. Okay. And so these are basically only for surfaces that are concave. Okay. And so as an example, let's say that we have a C geometry, okay? And so, we have a geometry that looks like this. And so if we consider this curved part of the geometry here, we call this surface 1, okay? Then you can see, if that entire curved part of the geometry is surface 1, then if we have radiation that comes off from this point right here, right? The ones that kind of come back towards the inner bend right here, that's going to radiate on itself. Okay. Right. This one as well. Okay. And so in these situations with concave surfaces, then F11 is not going to equal 0. Right? We don't know what it is yet, right? I think there's not enough information here to determine what that is, but at least we know it's not 0. Okay. On the flip side, if we have a surface that's by the opposite of that, that's either flat or it's convex, then we say it's not possible for that surface to radiate itself. Because remember, radiation can only travel in a straight line, so it can't curve back, right? So it can't make any turns. And so you have a surface like this, right? Or if you have a surface like this, where we consider the upper half, right? We do our radiation that's coming off of here. Okay. Same thing on the top here. There's no way for those radiation rays to kind of hit itself, right? Because they're coming off straight off the surface. Okay, it's only possible for concave surfaces. Okay, and so what we can say is that by inspection, right? By inspection from these situations, then FII has to equal 0. Okay. Okay. And so that's one instance where you would use this kind of inspection. It's not really a rule, but it's, I call it a rule just to be consistent with the other ones. Okay? And so if the geometry is such that it's kind of obvious to state, one of these things, then what you can say is by inspection, then, we say that this is equal to 0 or it's equal to 1, something else. Okay. And so in the next example, we're going to, I'll show you kind of another case of that. Okay. Okay, so just kind of be on the lookout for these situations where you can kind of determine a view factor just by inspection. Okay, and so by these 3 rules right here, what you can do is you can take a situation you can take a radiation situation and determine all the view factors. Okay, and oftentimes when you're considering radiation exchange, getting all the view factors is usually step one towards your analysis. Okay? All right, any questions on this? Okay, all right, so let's do an example to kind of show you kind of what this process is like. So as an example. Okay, so in this example, let's say that we have two surfaces, okay, and so we have an enclosed cylinder. Okay, so it's almost kind of like our concentric tube heat exchanger. Okay, let's say that we have a surface like that. We'll call that the outer cylinder, and then we'll call this one the inner cylinder. Okay, except we're not going to consider any flowing fluid, so let's just say that this inner cylinder is solid. Okay. We'll call the inner cylinder surface 1, and we'll call the outer cylinder surface 2. Okay. And what we want to do in this problem is, we don't have any temperatures here, but what we're going to do is we're going to compute all the view factors in this situation. Okay. Okay. And for two surfaces like this, we actually have 4 view factors that we need to determine. So we have F12, okay, F21, of course, right? And so those are the view factors of the surfaces themselves going to the other ones. Okay. We also have the self view factors as well. So we have F11 and F22. Okay. And so we're going to use our 3 rules here to determine what those view factors are going to be. Okay, all right. So let's start with the inspection ones. And so let's see, which ones we can determine just straight off the bat. Okay, so let's start with F11. Okay. And so F11 here determines, how much radiation that surface 1 is going to emit that comes back to surface 1. Okay, surface 1 here is a solid cylinder, right? And so we're only going to consider radiation that comes off the outer edge. Okay. Just like that. Just wanted to draw radiation lines, and I messed everything up. Okay. All right. So what do we know? So what do we know about the outer surface of the cylinder? Right. We know it's convex, right? And so there's no way for the radiation to kind of bend over and hit itself without hitting 2 first. Okay. And so what we can say is that by inspection, F11 is going to equal to 0 because surface 1 is convex. Okay. Okay. And so that's one that we know kind of right away. Okay. Okay. And so F11, we know kind of straight away. All right, so next let's do F12. Okay. And so to determine F12, the rule that we're going to use here is the completeness rule. Okay. Because by the completeness rule, if we sum up all of the view factors that come off surface 1, right? So that includes F11. And in this case, we only have one other surface, which is F12. Okay. Okay. You sum those up; those have to equal to 1. Okay. We can use this to solve for F12 because we know F11 already. F11 is just 0, right? We determined that by inspection. And so what's left here is that F12 is going to equal to 1. Okay. Right, so F11 is equal to 0, F12 is equal to 1. Okay. Next one we're going to determine is F21. Okay. And the rule that we're going to use for this, well, let's check. And so let's check the completeness rule first. Okay. And so under the completeness rule, if we do this for surface 2, and we say that F21 plus F22, their summation is going to equal to 1, right? And so we apply the same rule as surface 1. Okay. Unfortunately, this is not useful to us yet because we don't know F22 yet either. Okay, so both of these are unknown. Okay. And so this is not useful to us yet, but it will be useful to us soon. Okay. All right, so the next one we're going to check is inspection. Okay. And so is there anything from this geometry here that lets us determine either F22 or F21 kind of right away? Okay. And so based on the geometry here, since surface 2 here is the enclosing surface, right? Oh, and I guess backtracking a little bit, the reason we can use completeness rule here is because we have an enclosure, right? And so in this case, surface 2 kind of encapsulates this entire situation. And so we have a closed situation. Okay. All right. And so let's see if there's anything we can do based on inspection, right? And so surface 2 here, we can see it's concave, right? Because it's we have radiation coming off from the inside. And so it's actually possible for surface 2 to radiate on itself, right? And so let me trace one beam here. And so it's very possible for surface 2 to completely miss surface 1 and then just radiate on itself, right? And so you can come up with lots of different examples of this. Okay. And so we know that F22 here is going to be non-zero. We don't know what it is yet, but we know it's going to be non-zero. Okay. Okay. And so since F22 is non-zero and we can't determine what it is, inspection is not really going to be helpful for us here as well. Okay. All right. So completeness is not useful yet. Inspection is not useful. And so that just leaves our last rule here, which is our reciprocal rule. Okay. And so our reciprocal rule basically says that if we want F21, we multiply by A2, okay, this has to be equal to F12, A1. Okay. Okay. So this one here is actually going to be useful for us because we know F12 here is 1, right? We determined that in step 2. And A1 and A2, those are just going to be the surface areas of the given cylinders. Okay. And so, I neglected to give it to you, but let's pretend that we have the diameters. Okay. And so if we have the diameters, then the surface area for surface 1 is going to be pi d1 times L. Okay. L being the length of the cylinder that's going into the page. Okay. That means A2 is going to be pi d2L. Okay. All right, so let's go ahead and plug these in. Okay, so we'll have F21. Right, we multiply that by A2, and so A2 here is going to be pi d2 times L. Okay. On the right-hand side, we multiply by F12. F12, though, we know is 1. Okay. And we multiply by the area of cylinder 1. Okay, so that's pi d1L. Okay, so we can go ahead and simplify this. And so we have pi's on both sides, and so we can cancel those out. We have L's on both sides, we can cancel those out. Okay. And so we get F21 is simply equal to, we divide both sides by D2. F21 is just going to be the ratio of the diameters D1 divided by D2. Okay. And assuming that you know what those diameters are, and so let's say that D2 is 10 centimeters, D1 is 5 centimeters, then we can see here that F21 would be just the ratio between those two. Okay? 5 over 10, 1/2. All right. Of course, you don't have to go through this whole kind of song and dance. And so if you kind of know already that you have F12, you can just jump straight to the reciprocal one. But I kind of wanted to walk you through kind of the thought process of, first let's check inspection, first let's check completeness, right? And if all of those fail, then we can use the reciprocal rule at the end to determine our relationship. Any questions on this here? Yeah. Yeah, we're going to do that one next. Yeah, I have another example. Okay. All right, but before we do that, we have to kind of complete this. And so we have F21. And so the last one here is F22. Okay. And we can come back to a relationship that we saw earlier that we didn't know yet. Right. And so let's use our completeness rule again. Okay. And so our completeness rule says that F21 plus F22 is equal to 1, right? So all that has to sum to 1. We know what F21 is because we just solved for it. And so this is just D1 divided by D2. Okay. And so we solve for F22. F22 is simply just going to be 1 minus D1 divided by D2. All right. And so that's, it's a fairly simple example. And of course, it's one where the surface was already closed, but that kind of walks you through kind of the process of how to find these view factors. Okay. All right, any questions on this? Yeah. No, it's a ratio. And so it's a number between 0 and 1. Yeah. Mm-hmm. Yeah. And so, this, I kind of showed you kind of the whole thought process here. But if you can find some by inspection and then, just very quickly go through the rules, then that's okay. I would like you to kind of explain just a little bit of kind of what you did, but you don't have to show all the equations like this. Yeah. Mm-hmm. Okay. And so those are the 3 methods. Okay. If all else fails, you can look up, there are some view factors that are tabulated in the book. And so if you're totally stuck on a problem and you can't determine what the view factors are, I would check these tables to see if the geometries here are useful to you. And so there's two of them. And so there's table, it should be the first table in chapter 13, and so it should be table 13.1. Okay. And so I believe these are for 2D situations, which is what we're going to be mostly doing in this class. But there's also 13.2, and 13.2 covers some 3D situations. I believe that's how they're organized. Okay. And so I don't remember, you might have to refer to one of these tables for the homework problems. And if you, I know we're all thinking with the final. And so if you do need the information from these tables on the final, then I'll just give those, I'll give those to you. Okay. All right. And so that's the view factors. And so, the question is, how do we actually use them in heat transfer problems? And so we're going to do them in, in kind of a simple case first. And so we're going to do this for black body radiation first. And then, starting on Wednesday, we'll use them for more realistic surfaces. Okay. Okay. And so this is where we're kind of bring things back to heat transfer. Okay. And so the first thing we're going to do, or the first kind of situation that we'll cover in terms of radiation, is two black bodies kind of exchanging heat with each other via radiation. Okay. All right, so we start with this case, because we don't have to worry about emissivity or absorptivity, right? So we know that the surfaces are going to be perfect radiators, right? And so it's going to emit radiation with perfect efficiency, and it's going to absorb radiation with perfect efficiency as well. Okay. And so in this case, we ignore X of epsilon and alpha. Right, because we're going to assume both of them are equal to 1. Okay. And so, let's consider the case of two surfaces first. Okay, so let me draw our same situation for before. Right? And so we have our potato I, and we have our Planck friend J. Okay. We can write out the view factors, right? And so if we say that, Fij is equal to Qij divided by Ai, Ei, okay? And then the reciprocal relationship, Fji is equal to Qji divided by Aj, Ej, okay? Let me go ahead and plug in for E and both E's here. Okay. So we can say that Fij is equal to Qij divided by Ai sigma Ti to the 4th. Okay. All right, so all I've plugged in is just the black body emissive power. And then we have the same thing for surface J as well. Okay. All right, let me solve both expressions for the Q's. And so we have Qij is equal to Fij Ai sigma Ti to the fourth. Then Qji is equal to Fji Aj sigma Tj. Okay. So remember how these Qs are defined. And so Qij is the radiation that passes, the radiation heat transfer that goes from surface I to J. Okay. And on the flip side, Qji is the radiation heat transfer from J to I. Okay. And so if we take the difference between these two, right? So we take the difference between Qij and Qji, that is defined as the radiation exchange. Okay. Because that's how much heat is being exchanged via radiation. Okay? And so what we can say is that Q exchange is equal to Qij, and it doesn't really matter which one you put first, because the sign will take care of itself. Okay? Right? And so the sign convention uses the same as we've done before, right? And so if you compute this and you end up with a positive number, that means the heat transfer is going in that direction. Okay. But if you get a negative number, that just means heat transfer is going in the opposite direction. Okay. And so let's go ahead and plug in for these. And so if we have Qij, this is Fij Ai sigma Ti to the fourth, okay, minus Fji Aj sigma Tj to the fourth, okay. Okay. And so that's fine. And so that right there is a fine definition for radiation exchange, but it's a little bit messy, right? And so there's kind of a lot going on. And so we can clean this expression up by using our reciprocal rule from before. Okay. So let me circle these two quantities here. Okay. And so we can say that this Fijai, this is equal to Fji Aj. Okay. And then on the other side, Fji Aj is also equal to Fij Ai, okay, and these are by reciprocal. Okay. And so you can substitute one or the other, okay, and then it's going to clean up this expression quite a bit. Okay. And so our final expression for Q exchange, okay, we have two forms, and so we have one that's in terms of I, so we have Fij Ai, okay, and so if we substitute for the second expression, then this is going to be equal to sigma times the difference in temperatures, Ti to the fourth minus Tj to the fourth. Okay. And so that's one way that we can express this. Okay, so that's if we substitute for the second one, or say that Q exchange is equal to FJI AJ sigma. And again, TI to the fourth minus TJ to the fourth. Okay. And so either one works. And usually you want to put it in this form because, you know, if you this lets you just compute one of the view factors, right? And so usually one of the view factors is easier to compute than the other one. And so if you compute one of the view factors and you know their surface temperatures, then you can compute the amount of heat they're exchanging via radiation. Okay. All right, any final questions on this before we wrap it up for today? Okay, so I do have one more example, but I think we're not gonna be able to finish in time. And so let me go ahead and call class early so you guys can come up and pick up your midterms, okay? All right, and so I think this might be enough to kind of get you started on the homework. Maybe you want to wait till Wednesday before we do an example. But you know, we basically have this example. We have one more kind of big set of lecture notes, and then that'll be it for the class. All right, so thank you guys for coming today. You know, if you're here, you can come pick up your midterms. If not, you know, if you guys are here virtually, I'm going to bring them again on Wednesday, so you can pick it up then. Or just like the first midterm, if you can't come to campus over the next 2 weeks, just shoot me an email and I can scan your exam. Okay? All right, so thank you everybody for coming today. I hope you guys enjoy the rest of your afternoon, and I will see you guys on Wednesday. Ozzy, you want to put the rest of the file on there? Okay. Yeah. So there are 2 days. So you can either do next Thursday at 9 a.m. It seems like Ryan and Brett don't want to do that day. And so we'll probably do next Friday. Yeah, because I know you guys are taking exams with Dr. White. But her, for them, okay. But her exam takes place after mine, kind of normally. And so I'll let her have the Monday, and then we'll do the Friday. Awesome. So I should be free pretty much the entire day Friday. And so I would prefer that all 3 of us should have the same time. Yeah. And so if the 3 of you can come up with the 2-hour slot that works for all of you, then let's do that. Awesome. Yeah. Yep.
Yeah, I have my physics B, I have to design an experiment.
Okay.
I was wondering if do concentric heat exchangers. So if I have the flow, the inner flow going,
You can ask him about
this direction,
Yeah.
would that change?
I believe not.
It doesn't, it's the only thing that matters if the 2 fluids are going the same direction or they're opposite. So that's the only thing.
Would that differ the outcome? Effectiveness?
It shouldn't. I mean, it's going to change where your inlet. Yeah. The inner fluid comes from this side. So the inlet temperature comes over here. Yeah.
There's not a mirror, it's in this back.
But you should get the same result. It depends on what direction. And so the outer one is matching the outer one also is and both your colors are the same place. That would be parallel flow. But if your outer flow is coming from the other side, then that would be counter. So it just changes the equations that you use, but the result is right now.
I don't know if that makes sense for the experiment.
You can try, well, I guess I don't know the name. You can compare parallel and counter. Although maybe I should, I don't know what the experiment is. Okay. Yeah, I think it'd be interesting to compare, you know, like parallel flow with counter flow. Especially if you compare them.
Yeah.
And so you can compare that. If you have all the equations of parallel and counter.
I lost it.
Cutters. Congrats.
Brother.
Oh, yeah. Which one? Oh, yeah.
Here we go.
anything that I didn't.
Yeah, turns out that's next week, so.
Yeah.
We'll see how that goes. I still haven't talked to all my professors yet, but other people in the class I know it's tag along. For the most part, it's just
It's
project.
gonna be too bad to get it.
Yeah. Yeah, I mean.
Oh. Did I get?
I just ran out. A lot of my classes.
No.
Yep. Mhm. Yeah, let me know when you guys find a time.
Yeah.
Yeah, and then for you, you know, get longer time.
Yo, would I come earlier or?
Either works. You can either come early or you can stay an hour. Whichever works. I should be free all day, so I can do.
To come to your office, right?
I might have to rent a room because I don't have 3 seats in my house.
Oh, that's right.
And so, I'll arrange that. So first, let's find a time slot, and then I'll find a room.
Yeah, I shouldn't have anything on Fridays.
Okay, yeah, just discuss amongst yourselves, and then whatever time slot. I'll find a room.
Okay.
Yeah.
Thanks.
Mhm. Yep.
I was hoping to pick your brain about it.
Okay,